Hi, welcome to this session. I'm Changjiang from NS Studio. In the next 15 minutes, I will introduce a work about minimizing energy cost with reliability and throughput constraints. We target streaming applications that appears in multimedia and other domains. They are delay sensitive and need a high reliability. For example, in self-driving cars, the reliability and performance is crucial. The computing platforms for running streaming applications are composed of a two-level communication system. Some of them are battery-operated, hence energy efficiency needs to be considered carefully. So in this work, we try to minimize energy cost under throughput and reliability constraints. Streaming applications are modeled as serious parallel graphs in this work. Each node represents a computation task. Edges between tasks represent data dependencies. As shown here, the simplest SPG is two nodes connected by an edge. Then any SPG can be formed by a serial or parallel compilation of small-size SPGs. The hierarchical computing platform we considered has C blocks. Each has P processors. Each processor has an independent dynamic voltage frequency scaling capability. It can select its execution speed from a given set. It subjects to software errors. All these cores are connected by a two-level communication system. Processors in a block are connected by bus with bandwidth beta 1. Then blocks are connected by network on chip with bandwidth beta 2. Communication inside a block is more faster than that between blocks. For the purpose of node balance and saving communications, we partition the graph into many parts. For the ease of communication pattern, the partition has to follow the structure rule. The resulting parts should either be a single task or a small SPG, or several SP subgraphs that share the same predecessor and successor. Let's see three examples. In the first example, the partition splits a chain into many connected parts. In the middle example, the fork node itself forms a part. The same for the sink node, it forms a part. Since nodes between them share the same predecessor and successor, they can form several parts. The example on the right-hand side consider more cases. After the partition step, we allocate parts onto a core or onto three cores of the same block. All cores are prone to software errors, especially when operating at a low voltage. We follow the classical failure rate model, and the failure rate at maximum speed is of 10 to the minus 5 order. If we triplicate a task, even running at the minimum speed, the failure rate of 2 copies is very small, which is of 10 to the minus 7 order. Hence, we assume that running at the maximum speed or running with 3 copies is reliable enough. A very small failure rate is acceptable in this work. Let's say the energy cost. We model the energy cost as a sum of a static part and a dynamic part. The static part is a static leakage current is the static leakage current times the minimum voltage. The dynamic part is a product of the work node and the square of frequency. In the case that the static part is small, triplication can be energy efficient. An example is given in our paper. We further consider the energy cost on communication. It linearly correlates to the size of data to be transferred, and transfer data between blocks is more expensive than transferring it inside the block. Let's see how do we model the time spent on executing tasks. We consider time spent on each core and the communication. The first term is the time spent on executing all tasks allocated onto core V, and the communication time for majority voting if it's triplicated. The second term represents the communication time for sending out datasets. The third term represents the communication time for receiving datasets, and we take the largest one. For the time of executing a data on the whole workflow, we just take the maximum of time spent on all cores. Our target is thus to make sure the execution time is not larger than the period. Now we can formally define our optimization problem as mean energy. The decision version of the mean energy has been proven NP-complete. Thus, we put our efforts on finding efficient heuristics for general cases or optimal solutions for specific cases. For specific cases, linear chains, we proposed a dynamic programming method. We recursively express the minimum energy of running tasks T1 to tasks Ti as function E. In this function E, the K ideal is consider all possibilities and select the minimum one. Let's say an example. Now the aim is to schedule the gray part, task T1 to task Ti, and we have 6 cases. The first part is that we do not break any edge. It results a gray part. We run all tasks on a core with maximum speed, or we run all tasks on 3 cores of a same block. The second part is that we break an edge. Let's say we break an edge between task Tk and task Tk plus 1. So it results 2 parts, the orange part and the green part. We run the orange part in the minimum energy cost way, and then there are four possibilities for the green part. We can triplicate the green part on the same block as the orange one, or triplicate it on a different block. Or we can run the green part with the maximum speed on the same block as the orange one, or we can run the green part with maximum speed but on a different block. And we continue the part 2 recursively on the orange part. In this way, finally we can express the minimum energy cost. Unfortunately, it is not optimal, but we proved that it's optimal for the monotonically mapping. By monotonically mapping, we mean that if we assign tasks T1 to Tn, then blocks assigned to task to T1 to task Tn should also increase or decrease monotonically. In this way, dynamic programming is optimal. For the general cases, we designed the heuristic max speed as a baseline heuristic. It executes all tasks at the maximum speed, and then it greatly maps tasks to cores. It assigns tasks in a depth first way, and it maps tasks onto the current core as long as period bound is respected. It prefers the current block, and then if there are no cores available, it will move to the next task, next block. Group cell partitions graph G in a bottom-up way. It first breaks all edges except those that are too big to be transformed between blocks. Then it selects the most energy efficient way for all parts. Either we run a part at the maximum speed, or we run a part with 3 copies. And then we check how many processors we need. If we need too many processors, we have to merge neighbor parts inside the vector of maximum speed. If it still needs too many processors, and then we need to merge parts in the triplication vector. Break fork join DP, it partitions graph G in a top-down way. It breaks all input edges of join nodes and the output edges of fork nodes. So all the resulted parts are linear chains right now. Then we call dynamic programming on each linear chain, but we do not use the mapping phase of the dynamic programming. For mapping parts onto blocks and processors, we have 2 heuristics, map rank and map topology. Map rank first maps parts that are connected by large edges. They will map them onto a same block. The first step is we put parts connected by a big edge into a set, and then we check the number of processors requested by parts of this set. If it demands too many processors, we have to set some parts run at the maximum speed to reduce the request of processors. Map topologies maps parts following the topology order. It maps the current part onto the same block as its first predecessor. If the input age is too big and not enough processors exist on the current block, we will move some parts that are already mapped onto the next block, and then we continue the mapping on the next block. To test our heuristics, we conducted an extensive simulation. We selected 44 applications from Streaming It benchmark, and 10 of them are chains. We base the characteristics of our core on the Intel Skylake SP processor, and we set several levels of communication cost. So with a larger CCR ratio, the communication cost is more expensive. And we also set several levels of period bound. With the parameter kappa, with a larger kappa, the period bound will be tighter. Let's check the results. Those two figures show the number of cores requested by heuristics, so that the heuristic can find at least a valid scheduling. We can find that the break fork join DP, it requests larger number of cores than other heuristics, and then the second one is group cell. Those two figures show the energy cost normalized to max speed. We can find that on linear chains, break fork join DP and DP reduce the energy cost by around 44%, and on general SPGs, break fork join DP and group cell, they save more than 50% of energy. Let's check the failure rate. Those two figures show percentage of failure cases. On linear chains, the group cell fails more than other heuristics, and on general SPGs, break fork join DP fails more than others. In this work, we model running series parallel graphs on hierarchical platforms to minimize energy cost with throughput and reliability constraints. We partition the SPGs to reduce the communication and processor request. To make sure the reliability is guaranteed, that we run tasks either at the maximum speed or with 3 copies. And we proved that this optimization problem is NP complete. So we have to design efficient heuristics. We proposed dynamic programming for the linear chain case, and in some cases they are optimal. And we designed some heuristics for general cases which have been proving efficiency through simulations. And in the near future, we plan to investigate if the dynamic programming is an approximation algorithm or not. Thanks for your attention, and any question is welcome.